Welcome, everybody. So this is lecture 14 in this course on models of quantum computation. And today we begin to talk about measurement-based quantum computation. This will concern us in the next couple of lectures, and this is the first of them. Okay, so here is a grid of qubits, and they have been prepared in a two-dimensional cluster state. You will very soon learn what a cluster state is. We haven't defined it yet. Maybe you know it, but anyway, it's a grid of qubits entangled in a particular way. And so now that we have this thing, by local measurements, we can create a bunch of stuff. So here's the first example. So you have two qubits here, qubit A and qubit B, and you want to entangle them in a Bell state, say, no matter how far these are separated, A and B, where they are located. You can do that. And you can do this by local measurement. And this is shown here. So you make this channel from A to B, and this channel is made of measurements in the eigenbasis of Z and measurements in the eigenbasis of X. And after you've done that, you have created a Bell state between particles in A and B. After you've done these measurements, you have that Bell state. Okay, so this is one thing you can do. You can create a Bell pair between any qubits here on this cluster, on this two-dimensional grid. But that's only one thing you can do. You can do lots of other things. So yeah, I think I talked a little bit about the surface code. Surface code is a quantum code. It's actually, in many ways, a very good quantum code. Yeah, we looked at this code in this lecture series for something between 2 and 5 minutes. Not very long, but at least you've seen it. And you can make a surface code from a cluster state. You just have to measure half of the qubits in this checkerboard pattern. Yeah, you apply Z measurements and X measurements on in total half the qubits, and you get the surface code on the other half. So this is something that you can make with the entanglement in cluster states. And now that you've seen these examples, maybe you ask yourself, how far can we take this? And there's pretty far, actually. So here's the first thing. So the two-dimensional cluster state is a computationally universal material. You can make any quantum computation on it by one qubit measurements only. Okay, and if you want to do the same fault tolerantly, then you can go one dimension higher up. You can do fault tolerant universal quantum computation with three-dimensional cluster state. And we will also look at that briefly. Briefly, because fault tolerance isn't really in the center of this lecture. But we'll talk about it. Okay, and so here is an outline of this part of the lecture that is concerned with measurement-based quantum computation. So what I will begin with is an overview, just kind of where measurement-based quantum computation stands and what it is good for. And then come the technical parts. And so the technical part we will do today is computational universality, the proof of computational universality. And then what comes up thereafter is fault tolerance, then contextuality in measurement-based quantum computation. That's part 3. We already saw contextuality discussed in quantum computation with magic states. So here we have a counterpart for that. Then fourth, computational phases of quantum matter. So this is concerned with the question, what besides cluster state, what resource states exist that enable universal quantum computation or quantum computation of some power. Then there's a fifth part, although we will discuss that separately, and this is quantum computation with probabilistic heralded gates. So we'll do this after KLM, after the KLM scheme of linear optics quantum computation, and we do it thereafter because it's really an application of that. Okay, good. So these are the 5 things we will learn in this course about measurement-based quantum computation. Okay, so the overview section In its own has three parts. So the first is measurement-based quantum computation in a nutshell. Then we will talk about cluster states. We will define what they actually are. And I also give a very brief overview over experiments. Okay, so let's get started with that. So first, there's two types of evolution in quantum mechanics. There's unitary evolution and projective measurement. They are very, very different from one another. Unitary evolution is deterministic and reversible, and projective measurement is probabilistic and irreversible. So let's take this apart a little bit. Deterministic evolution, deterministic unitary evolution. Yeah, so you apply Hamiltonian for a certain amount of time that implements a unitary, and in principle, the unitary has an inverse, and so you can undo it and get back to exactly where you started. So it is reversible. For projective measurement, that's not the case. So first, it's probabilistic. You measure, you get an outcome. You don't know what you're going to get. It is according to certain rules of probability. Yeah? You can roll dice, but you never know what's going to happen in a particular instance of an experiment. And also, once you've done the measurement, you can't go back. So look at this in this example here. So you have a one qubit state, so we can visualize it on the Bloch sphere. So that's your state. You do a measurement of the Pauli observable Z, sigma Z, and you end up either here or here. And once you have projected the state into one of these two alternatives, you don't know where you came from. It's impossible to go back. Yeah, so it's irreversible. This measurement is irreversible. Unitary evolution was reversible. So very different. It turns out, however, that from the perspective of quantum computation, you can do the same things with both of these. You can do quantum computation based on unitary transformation that leads you to the circuit model, or you can do it using projective measurements, and then you get to measurement-based quantum computation, which is what we are going to discuss. Computationally, power-wise, they are equivalent. Either of these models can simulate the other efficiently. Now, there's no unitary evolution. We're just compute by doing measurement. And so here you have the 2D cluster state again, and now you can implement certain measurements on the qubits here, and what you can choose in a measurement, first what you cannot choose is the outcome, but what you can choose is the measurement basis. Measurement basis you can choose. And so now depending what choices you make for the measurement basis, you tell the cluster state to implement this or that quantum algorithm. So the algorithm implemented is a function of the measurement basis. First, regarding the state, the cluster state, which we have yet to define, is a universal resource. So that's a non-trivial thing. Is there at all a quantum state that allows such a scheme of computation? And there is. And cluster state is one of the universal resources that have been figured out. And so once you have that, now again, no unitary evolution taking place. Information is written onto that cluster, processed and read out by the one qubit measurements only. It's the only physical operation that happens. So this is measurement-based quantum computation in a nutshell. And I think the graphics here is quite suggestive. Yeah, so you have these dots here. By the way, this represents measurement in the Z basis that does something. And then you have the remainder that already looks like a network. So maybe this is a network of gates. So indeed, that's the case. So what you see here, first these horizontal lines, these are qubit wires going from left to right. Then these vertical lines in between, they mediate interaction between these logical qubits. Yeah, so that would be a CNOT gate in this case. And then if you change the measurement bases in certain ways, then you can do rotations. So what you see here expressed in this picture is how you simulate a quantum circuit in the scheme of measurement. So this is indeed the graphical view of the universality proof, and that we will now be going to look at, oh well, later actually, not immediately, but later today, yeah, we are going to look at that in all detail. Good, but let's continue with the overview. So a few characteristics of measurement-based quantum computation. So measurement-based quantum computation, here often abbreviated as MBQC because it's a long word. Yeah, it has an appetite for qubits. So yeah, so here you see a 2D cluster state. It simulates a quantum register kind of on a one-dimensional subset of this 2D grid. And so you see this is the number of qubits you need in the circuit model. This is the number of qubits that you need in measurement-based quantum computation. So number of qubits in MBQC is number of qubits in the circuit model times number of time steps. Okay, so MBQC uses much more qubits than the circuit model. That's a flip side. And there's something we can do about it. Yeah, so you can reuse qubits. So this is what's shown here. So you make a cluster state, you use the cluster state for computation. This is local measurement. So the qubits that have been measured, they are kind of freed from the cluster state. They are no longer entangled with it. And so you can bring them around and on the other side, reattach them to the cluster state. So you have some sort of conveyor belt architecture where you shrink the cluster state on one side by performing the measurements that drive the algorithm, and on the other end of the cluster state you attach more cluster states so that you can do more computation. So that gets rid of this qubit overhead mostly, if that's a primary concern of yours. Good. So now what is measurement-based quantum computation good for? So related to what we've just seen. So if you have quantum computation with probabilistic heralded gates, so here there's a certain entangling gate, and we'll see this shortly, that you can use to make more cluster state, that you can use to append to an already existing cluster state. And now assume that this entangling gate is probabilistic and heralded probabilistic. So it sometimes succeeds and sometimes fails, but in every instance you learn whether the gate has succeeded or not. Okay, then there are certain ways, if that's the situation, that failure isn't quite as bad as non-heralded failure. And so you can use this. And if your success probability is sufficiently high, you can grow cluster state on one end on average. And you do this at some safety distance from where you're using the cluster state for computation. Yeah, and that gives you an efficient way of quantum computation with heralded gates. So a priori, heralded probabilistic gates are detrimental. Yeah, so the probabilistic nature is detrimental, but here you have a way of mitigating that effect. Okay, so a natural scenario where probabilistic heralded entangling gates come up is the KLM scheme of linear optics quantum computation, which we'll discuss later in this class. And yeah, and the cluster state model helps you to drastically reduce the overhead of that scheme, the computational cost of that scheme. Okay. Another thing that measurement-based quantum computation is good for, that is for secure delegated quantum computation. So let's assume this is you and your modem. You have a very limited quantum device. Your modem can create 1 qubit states, one at a time, unentangled, and then you talk to a server. So this server is all powerful, can do all quantum computations, yeah, fully universal, fully fault tolerant, but not particularly trustworthy. So you, with your tiny little modem, you want to delegate a quantum computation to that server, and you require two things. You you do not want the server to learn what you are computing. That's the first thing. And also, you do not want the server to cheat you. You want to make sure that the server does indeed compute what you want it to compute. So that is secure delegated quantum computation. And that is possible in the quantum world, and that has been shown by Anne Broadbent and company here in this paper. Yeah, and so that is based on measurement-based quantum computation. So this is another thing that MBQC is good for. Distributed quantum computation. As we'll see later, the three-dimensional cluster state is inherently fault tolerant, and that is nice for fault tolerant distributed quantum computation. Good. Okay, so that is the end of that review, and we now get a bit more technical. Cluster states, creation. So now, yeah, cluster states came up here quite a bit. They are the resource states that we are considering. Remember, we had a resource state in quantum computation with magic states. Now we have a different scheme of quantum computation. Still, there is a resource state, and that resource state is now stabilizer. It's a stabilizer state, as we are going to see later, and it is entangled. So quite the opposite of the state we had in quantum computation with magic states. Okay, so we will give the formal definition later. So we begin with a way to create it, a creation procedure for these states. Okay, so we can create cluster states in two steps. The first step is we prepare every qubit individually in an eigenstate of sigma x. Yeah, so these qubits may live on a d-dimensional lattice. Okay, and every one of these qubits is prepared in an eigenstate of x. So then we apply the Ising interaction. So that's that thing here. Nearest neighbor interaction, Ising type. We apply this for a fixed time. And this time t is independent of the dimension of the lattice or what kind of lattice it is. It's just, yeah, it is fixed. And after this Ising interaction has been applied for that fixed amount of time, then the creation of the state is finalized and the unitary interaction is switched off. Okay, so it's an important point to note that the interaction time is fixed. It doesn't depend on dimension or anything. It's just always the same. Okay, so that is a way to create the cluster state, and that's kind of a useful picture for us also in proofs. So please remember that. I will use it. Examples. So let's start with a cluster state of 2 qubits, so that if you work it out, becomes this state here. It's an entangled state, and up to local unitaries, it is equivalent to a Bell state. Okay, that's the simplest cluster state. So now 3 qubits in a line that is a state that is up to local unitaries, equivalent to a Greenberger-Horn-Zeilinger state. Okay. Yeah, next example. So this is either this wheel-shaped cluster or it's a 3D grid with 1 qubit removed, whatever you would like to see in it. So 7 qubits at any rate, and that is a code word in the Steen code. Yeah. So what these examples are supposed to show you is that cluster states represent many states of interest in quantum information, quite naturally. So now we come to the proper definition of a cluster state. And as I already said, the cluster state is a stabilizer state. Yeah, on a 2D grid or 3D grid or whatever kind of grid, one-dimensional grid. Okay, we've illustrated here the two-dimensional case. So it's a stabilizer state, so there's a bunch of stabilizer generators, and here is what they are. So they come with a label A. A represents a site in the lattice, and the stabilizer generators have a Pauli spin flip sigma x on that site, and they have Pauli phase flips on all the neighbors. Yeah, so this is a stabilizer generator, so you can check that this thing commutes with all its translates. Yeah, so that is why these operators can generate a stabilizer. Okay, good. And then yeah, so the cluster state is the joint, it's the unique joint eigenstate of all these operators. Okay, so that's the definition. So we have a creation procedure and a definition. And now maybe you want to show that the creation procedure and the definition are actually equivalent. Good. Experiment. Okay, so I'm going into early experiments here only. I mean, yeah. So there's a few more. I mean, there would be plenty to discuss, but let me just mention the early and fundamental experiments. So here is an experiment made with cold atoms from the group of Immanuel Bloch with Markus Greiner here in front. So this is a paper from 2002, and this is with cold atoms in optical lattices. Yeah. And what they showed is that they can make cluster states. They verified the cluster state stabilizer in this physical setting, but they didn't use it yet for computation. They couldn't have, because in that lattice, the atoms were sitting quite close to one another, and when they would measure, they would use lasers, and they wouldn't have sufficient spatial resolution to address individual qubits in that lattice. But they verified that they had made cluster states. The first experiment of measurement-based quantum computation is from 3 years later, it's from 2005, and it was done by Philip Walter and company in Vienna. And this is now with a different physical basis. This is with photons. And they demonstrated that they could create 4-qubit cluster states and could do a universal set of gates on them, and then even ran a very small algorithm, namely a Grover search algorithm on a database with 4 items. Good. Okay, so I think this is it in terms of experiments. And yeah, so this concludes the summary. And I now want to continue with universality. So universality is the first part in the technical items that we want to discuss. So this is where this first part now stands in the overall structure of this part on measurement-based quantum computation. If we look at this part, well, there is just one item on the menu, and that's the universality proof. Okay, and so here's some reading for part 1. I mean, minimal reading. At the end of this lecture today, I'll give you a bunch of additional reading suggestions, but here's the minimal reading. So this is the original paper on the subject, and then when I explain gates today, I will refer to this paper down here. So they explain gates through a protocol that's called half teleportation. Yeah. Okay. You will see. Good. So now we need to think about how to organize the universality proof. So we will decompose the picture that you see here. So the first step in that regard is to analyze what the Z measurements here. Every dot that you see here represents a cluster qubit measured in the eigenbasis of Z. And we want to figure out what that does. Okay, so we take them out and we haven't really lost anything. So measuring in the eigenbase of Z essentially removes these qubits from the cluster. And so the remainder of that looks already like a network. Now, so you can imagine qubit wires, gates. Okay, yeah, so that looks quite promising. All right then. And so next thing you want to do is chop it up into components. Yeah, you want to say, oh, this is a CNOT gate, this is a rotation, this is another CNOT gate, this is a piece of wire. And you want to explain all these gates. Yeah, first thing is wire. Fine, but then there are these random measurement outcomes. Yeah, so we've learned that, or we've discussed it some time ago. In a quantum measurement, you can choose the basis, but you cannot choose the outcome. And so the question is, does this measurement outcome, this random measurement outcome, does it have an effect? And it probably does, for otherwise you could just trace over. And that is not going to give you any computation. So the measurement outcomes must have an effect, and we need to study that. And we will. So you want this randomness of measurement outcomes, you want to prevent it from creeping into the logical processing. Okay, so these are essentially the things we need to do. And in the proof, we do it in reverse. So here's the steps we'll do in the proof. Steps 1, 2, 3 is we look at the simplest gate, which is just the identity. And this is done by measuring cluster qubits in the eigate basis of X. Okay, so this is a complicated way of doing nothing. So next thing, here's a equally complicated way of doing something, namely of doing the 1 qubit rotations, yeah, by measuring qubits on the cluster. So that's the first thing that we'll talk about. And the third thing we would have to talk about is the CNOT gate, but I let you do it. Yeah, so these are the first 3 steps. There's 3 more. Okay, composition. We have to figure out, so when we compose measurement-based implementations of quantum gates, and yeah, when we do them, and then when we compose them, we need to make sure or prove that this is actually giving us the MBQC implementation of the composed operation. Huh? Yeah, that's something we need to show. And then, okay, so we need to indeed show that these extra qubits don't have an effect. And we need to talk about the random measurement outcomes, how to counteract that randomness. Okay, so these are the 6 parts in the universality proof. So let's go through them. Wire, first thing. Okay, so we do this the following way. So, so here first what you see is what we're going to do. So we have a 3-qubit cluster. So we have a cluster state with input here. I explain in a moment what that is. And then we do 2x measurements. And we want to show that this input is teleported to the unmeasured qubits. Excuse me, to the unmeasured qubit. Okay, so let's first explain what a cluster state is with input. What you see here is, I mean, if psi were a plus, then this would exactly be the creation of a cluster state. So the easing interaction that we had is now represented in more computer sciencey terms by a conditional phase gate. You remember conditional phase gate from earlier. It's an entangling gate like the CNOT. Okay, so if that were a plus, you would create the usual cluster state. But now we are talking about a cluster state with input, meaning we admit more general states here in the first qubit than just a plus. Can be anything. Okay, so this is the creation procedure of that cluster state with input psi. And then we have the 2 measurements. Okay, and we want to demonstrate now that this does what it is supposed to do, namely the teleportation to the 3rd qubit. Okay, so let's prove that. And we can prove this here in this cartoonish graphical fashion. So let's move from panel 1, which describes the situation, to panel 2. So the only thing that has happened here is that in this middle, we have inserted the Hadamard squared. Hadamard squared is the identity. So nothing has changed. Okay, and so now what we do in the next step, we take those final measurements and propagate them backwards in time past the conditional phase gate and past the latter Hadamard. Okay. And then we get here. So that is also something that you should be able to do, forward and backward propagation of Pauli operators through Clifford gates. So what we find is that this X measurement up here becomes the XX measurement here in this circuit. So upon backward propagation, that's the same thing. And this X measurement down here becomes the ZZ measurement upon backward propagation. Yeah. Okay. So much about that. And now, when we see this, we recognize that these two measurements here are nothing, I mean, in their combination, they are nothing but a Bell measurement. We realized furthermore that this part of the circuit, so preparing these two states in plus, conditional phase gate, Hadamard, that this prepares a Bell state. So the circuit we have here is equivalent to a circuit like this. So we have a Bell measurement and then we have some stuff, but because we have measured the system, we do not care about the quantum operations thereafter. Okay, so we have a Bell measurement here, and it is applied to 1/2 of a Bell state in an unknown quantum state. And that is, modulo the classical post-processing and correction that we haven't shown here, is a teleportation protocol. Okay, so this is indeed what happens. So the initial quantum state is teleported to the third qubit. This initial quantum state is teleported to the third qubit by a teleportation style protocol. Okay, so that was the first explanation of an identity gate. Good, so let's move on. Look at other operations, for example, 1-qubit rotations. Okay, and here, this is now where this half teleportation argument comes in. So let us look at the situation here. So it's basically the same as we had before, or similar thing, slightly more general thing. So we have the creation of a cluster state with input, but now the measurements are more free. So previously we considered measurement in the eigenbasis of X. Now we consider more general measurements, and we will see in a minute what type of measurements we'll actually choose. Okay, so the first step is just to change the temporal order of commuting operations. So if you see here, if you look at the conditional phase gate here and the measurement up here, the conditional phase gate is done earlier. But the gates commute, so we can switch the order, which is what we do. So over here in this equivalent circuit, that first measurement is done earlier than the conditional phase gate. Yeah, so we've just switched the temporal order. Likewise, we have switched the temporal order of that upper conditional phase gate and that state preparation down here. Okay, so we're just passing by one another commuting operations. Doesn't change the operation of the circuit. So this equals that. And now we see a certain block structure here. So we have a qubit coming in, 1-qubit state coming in, can be unknown. We do something to it. We provide another ancilla, entangle it, measure, and this block is now repeated twice. Yeah, so we have simplified a 3-qubit scenario to a 2-qubit scenario, yeah, concatenated twice with itself. Okay, and with this scenario, we now continue. So this is just what we've seen. So this wire-like protocol with more general measurement bases decomposes into two parts of the same structure. So now we specify these measurements up here. So The observables we measure will not quite only be x's, but they will be x's conjugated under z rotations. Yeah? So like shown here. Okay, so this is now what this half teleportation block amounts to. Yeah? So you have this conjugated observable measured after this interaction. Okay, and so this is equal to rotating with the unitary UZ just before the measurement. Yeah? So that is an equivalent circuit. So the measurement of this observable is like rotating beforehand and then measuring X. And now we furthermore see that the entangling gate, conditional phase gate, and that rotation, they commute. So we can move that rotation past the entangling gate backwards in time. So it is now acting right on the initial state, so the unknown processed quantum state. And so that's this gate acting first on something that we have already seen. Okay. Well, we have seen the concatenation of that with itself. So the block itself we have not yet seen. But this is now a very simple thing, just kind of stabilizer operations on a 2-qubit system. So you can easily compute what this does. And what it does is the following. So you take this state here, and this block does nothing but a Hadamard. Yeah, so we have this gate is applied first, then we have the Hadamard, and then we have a Pauli operator that depends on the measurement outcome over here. So we are familiar with that effect from the teleportation protocol. So there will be a Pauli correction operation dependent on the outcome of the Pauli measurement. And that's exactly what you see here. So this combined thing, unitary rotation that comes from the choice of measurement basis or measured observable, Hadamard gate, and Pauli correction. This triple of things happen when you apply this circuit. Okay, so here we go. That's the first rotation that we have realized. We have realized a Z rotation about an arbitrary angle, alpha, that just depends on the choice of measurement basis. And then we have this other stuff that we do not really care about, or that we do not really want, but have to deal with. The Hadamard and the outcome-dependent Pauli correction. Okay. So, okay, but, well, we want to do more than rotations about the z-axis. We also want to do rotations about the x-axis. And that now comes quite naturally. And to see that, we look at the concatenation of two such blocks, what they do. Yeah? Each block is like what we have seen. So it's the z rotation, the Pauli correction, the Hadamard. And what we now do is reorder these operations. So first thing to do is we are dealing with these Hadamards. Oh well, first we will move this Pauli correction to the very end. So conjugating by the Hadamard takes a z into an x. So this is what we see here. And then we will take this Hadamard and propagate it also towards the end. So the first thing that it does is conjugate the z rotation into an x rotation. Yeah? And then it hits upon, since this has been propagated out, it hits the other Hadamard and annihilates. And so this is what we find. So we have a z rotation followed by a z flip, conditional on the measurement outcome. And then we have an x rotation followed by potential x flip, conditioned on the second measurement outcome. Okay, so the upshot of this argument is we can implement both z and x rotations, and they are implemented in an alternating fashion. So if you have an odd, a qubit on an odd side, say, then it realizes a z rotation, and a qubit on an even side, say, realizes an x rotation. Yeah, so the location of the qubit tells you what rotation it implements. So here's the summary of this. X and Z rotations alternate, and we remember the Euler decomposition. So with a single Z, an X, and another Z rotation, out of these three blocks, I can build an arbitrary rotation in SU2. Good. So we are good as far as the one qubit rotations are concerned. Good. So that was step 2, the one qubit rotations. Now comes the CNOT. There's various ways of doing the CNOT. And you can maybe, you can maybe figure this out for yourself. So the easiest CNOT to figure out is this one. Let me tell you that. So here you have a hint for that. Arguing this CNOT is, I would say, quite a bit more complicated. So yeah, I leave it to you. And my recommendation is you start with the CNOT here on the right. Good. So overall, it's half teleportation tricks like the ones you have seen. So let's back up here. What we have done so far is we have explained the building blocks. Yeah? So we have explained how to do single qubit rotations and how to do an entangling gate. What remains in the proof is all the aspects that come from composition. And that is what we turn to next. Okay, good. So that's I just gave the summary. So here's the slide for the summary. We've done the gates, and now come the aspects of composition. So there's step number 4. We have to explain that measuring these qubits in the Z basis really just removes them. Then comes composition, and then comes counteracting randomness. Okay, so this is the remainder of this lecture. Cutting out networks, removing qubits by measuring them in the Z basis. Okay, so this is what we want to show here. So we only look at it in the instance of the simplest example. From there on, you can do the generalization yourself. Okay, so we have a 3-qubit cluster state, measure 1 qubit in Z, and yeah, so we want to show that this makes that cluster state over here. Yeah, so qubit is just removed. Okay, so here is how we can show that. So what you see here is 3 qubits prepared in the eigenstate of X, entangled with conditional phase gate. So this makes a cluster state of this 3 chain of qubits. And here comes the measurement we want to discuss. So this is a Z measurement with positive eigenvalue as the outcome. Okay, so now we want to transform this thing. Okay, so the first thing you've seen here is we take the projection corresponding to the measurement with positive outcome and propagate it past this entangling gate. And that's possible because, yeah, so this projection and that entangling gate commute. Yeah, now we look at what does the projection into the state 0 to that state in plus. Well, it replaces that state with the state 0. Next thing we look at is what this does. Yeah, so we have a conditional phase gate with a qubit that is in state 0. Yeah, there's nothing. So this conditional phase gate doesn't do anything when that qubit is in the state 0. Okay, so we have disentangled this qubit down here from the remainder. Okay? And so that's now the 2-qubit cluster state. Okay, so we have just shown this equivalence in this very simple instance. Yeah? So the upshot is the Z measurement removes the measured qubit from the cluster. So yeah, so admittedly, we have been looking at the simpler measurement outcome. So we didn't discuss the case when the measurement outcome is 1. Yeah, so that case is a tiny bit more complicated, but not orders of magnitude more, and so you can do this for yourself. Yeah, leave that to you. But the the upshot is the same. So if you measure that qubit with outcome 1, then you'll get the cluster state modulo a Pauli correction. Good. So this was step 4. We are done. Now, I mean, in this simple instance, now you maybe also want to generalize the argument to arbitrary configurations. Step number 5, composition. Yeah. So what we want to show here is that if we have MBQC implementations of quantum gates and concatenate them, that is, we concatenate the measurement patterns, that this combined pattern executes the combination of the gates. Yeah. Okay, so I have a measurement pattern that realizes a gate U1 and I have another measurement pattern that realizes a gate U2. Now I put them together, and what I want to show is that this combined pattern, stretching from left to right now, realizes the combined operation U2, U1 times U2. Okay, so in simple words, we want to show that MBQC gate simulations compose like the gates compose. Okay, that needs to be shown, and that's just another computation game. So let's play that. So here you have that. You have 2 concatenated MBQC gate simulations, one realized. So what you see here is a cluster state with input, and the first 2 measurements realize one gate, and the second 2 measurements realize another gate. Okay, so what we do is we change the temporal order of commuting operations, like so. Yeah? So these measurements up here commute with the entangling gates down here because they act on different particles. And likewise, the preparations down here commute with the entangling gates up there. Okay, so that is what has changed from the previous slide. Yeah? Exchanging the order of commuting operations. And now we see this is the gate simulation 1, this is the gate simulation 2. Yeah? Output of gate simulation 1 is fed as input into gate simulation 2. Okay, so that was composition. We have one more thing to think about, and that is counteracting randomness. So let me remind you, in a quantum measurement, the measurement basis can be chosen, but the outcome is genuinely random. Now the question is what to do about that. Will it affect the logical processing? Probably. What can we do about that? Good. Okay, so here you see in graphical form what's happening. So you have a cluster state, 1D cluster state here in this case, with certain measurement bases. So measurements in the bases shown are applied. So what does this mean? These are measurement bases between sigma x and sigma y, specified by an angle, a measurement angle. So you see this down here. So the measured observables are these. Yeah, okay. And that has the effect. So we've seen this before, that the measurement angles translate into the rotation angles. So we have a rotation about the z-axis and this measurement angle, qubit number 1. Then comes this random operation, yeah, that depends on the measurement outcome. Over here, we call this a byproduct. And then we've seen this before, Z and X rotation alternate, and then the whole game starts over. So we have all these heralded random Pauli matrices sitting here in the simulated circuit. So we do not want them, but we have them, and so we need to deal with them. And how this is dealt with, that we talk about now. Okay, so the overall strategy is that we take these byproduct operators and we move them towards the end of the computation, past the readout measurement. And everything that happens after the readout measurement, we don't care about. So once we have moved them past the readout, that's okay. So they do no harm. The point, however, is that they do harm on their way to pass the readout, and that we have to keep track of. So this is the overall strategy, and now we want to look at that in some detail. And so to simplify the situation, as an example, we look at the situation where we have just one single byproduct operator sigma x sitting here, and by virtue of the measurement outcomes, all these other byproduct operators have not appeared. So it's only one object to focus on. So we want to propagate it here past the end of the computation. Yeah, okay. So Pauli operator X anti-commutes with Pauli operator Z, and that effect we will see shortly. So we are propagating by one step, moving this thing over here. And because of, as I just said, the anti-commutation of X and Z means, so what we're doing here is we are conjugating this rotation under this Pauli operator. Oops. And so the effect is that we acquire a minus sign here in the rotation angle. And with this minus sign, this rotation is no longer the rotation we intended. So we will have to deal with that. Okay, so that was the first propagation step. So, but that's not the end of the computation yet. So let's propagate further. So here we have an X rotation commuting with this Pauli X, so nothing happens here. In the next step, we have what we have already seen 2 steps earlier. The Z rotation, the rotation angle is flipped into minus itself. Again, that's not the rotation we intended. And so now we further propagate that Pauli past the measurement. Nothing changes here. Measurement and Pauli flip commute. And now finally that Pauli flip acts past the measurement. So we don't care about it anymore. It's gone. But in its removal, this Pauli byproduct operator changed to rotation angle. So this is the effect that we need to take into account. We want to implement exactly the rotation angle we care about and not sometimes it and sometimes minus itself. Okay, so here's something for us to think about. That is the effect of the forward propagation of these random Pauli operators. And so now we observe the following. So the propagation effect on the relation between the rotation angle and the measurement angle is that the rotation angle that is really being implemented is the measurement angle, the choice of the measured observable specified by this measurement angle, times a sign factor plus minus 1 that depends on what the outcome was of the previous measurement. So the rotation angle is the measurement angle times a random sign factor plus or minus 1. Now, mathematically, this is equivalent to that. We just take the minus 1 to that power to the other side. And now what has changed is that so previously we had the measurement angle define the rotation angle. But now, and this is how we will use it, we have the rotation angle define the measurement angle. So we will adjust the measurement angle here for this observable depending on the measurement outcome we had obtained on the previous qubit. Yeah, and so now everything is properly deterministic. So we adapt the measurement angle according to earlier measurement outcomes, and then after propagation, everything is okay. We get exactly the rotation angle that we wanted. Okay, so to summarize, the measurement outcome at qubit number 2 influences the choice of measurement basis at qubit number 3. This is how we take care of randomness of the measurement outcome. But it has a consequence. The qubit number 2 must have been measured before qubit number 3 can be measured. Yeah, and so we see that the need to adjust to these random measurement effects, this introduces the temporal order between the measurements. Okay, good. So here is maybe the upshot of this whole thing. Outcomes of earlier measurements determine the basis of later measurements. And this whole adaptation business, first of all, gives temporal order to measurement-based quantum computation. Okay, so that is all we had to prove. This is the this is the universality proof in a nutshell, with the caveats that some parts we have only proved in special cases, and other parts we didn't do at all. So that remains for you to do if you want to. Good, but we are basically done with the universality proof. There's a few additional comments about counteracting randomness. So yeah, so here, so this is something that I already briefly alluded to. So the randomness of quantum measurement and the need to account for that in the logical processing implies the temporal order in measurement-based quantum computation. There's no a priori temporal order. So the randomness implies it, and it's kind of fun observation. Okay, and so now you may ask, is the temporal order in measurement-based quantum computation different from the temporal order in the circuit model? And the answer is yes. It's quite easy to see. So if you let's begin. So this is here what the adaptation of measurement bases does. So a measurement angle is flipped into minus itself or stays itself, depending on what the byproduct operator says. So that is the general procedure, and now we find that there's two bases, namely the x basis and the y basis, that are invariant under that flip. So first, the x basis, it is even pointwise invariant under this flip. Yeah, so the positive x eigenstate remains positive x eigenstate under the x flip, and the negative eigenstate is just the same. So there's no effect. Measurement basis doesn't need to be adapted. And if that's the case, then measurements in the x basis completely drop out of the temporal order. So now for the y basis, it is slightly more complicated. So under the x flip, the two eigenstates are being interchanged, but the basis of eigenstates remains the same. So physics-wise, there's nothing to adjust in such a measurement. It's always a measurement in the y basis. And so again, the y basis drops out of temporal order. And so the question is, what gates can we do with measurements in the x and y basis? And yeah, so the gates you can do are all the Clifford gates. So here are two examples shown, the Hadamard gate and the CNOT gate. Yeah, and all the Clifford gates, they completely drop out of the temporal order in measurement-based quantum computation. So yes, there is a difference to the circuit model as far as temporal order is concerned. Good. Okay, and this is in fact all I wanted to add to this aspect of temporal order. That's an addendum to the universality proof. I think it's quite fun. And I conclude with reading suggestions. So this is now a bit more than I had initially. So this is if you want to know more about the subject. So this is all for today. Thank you very much for your attention. Next lecture is going to be on fault tolerance. Maybe not the entire lecture. I want to keep that subject a little bit brief here. And then we continue with contextuality in measurement-based quantum computation.